Welcome back. Let us conclude our carbonyl compounds unit. But today we're looking at tests we can do to identify aldehydes and ketones. We're going to describe chemical tests can be used to test for and distinguish between the carbonyls present in aldehydes and ketones. The learning outcomes we're addressing just below there. We introduced previously the homologous series of the aldehydes and ketones, both contain that carbonyl group, that C double bonded to an oxygen, where the aldehydes have that at the start or the end of a hydrocarbon chain, whereas the ketones have that somewhere in the chain. We're going to look today at certain chemical tests that we can do to identify if we have this carbonyl present, and then to distinguish between both our aldehydes and our ketones. First test we're going to look at today involves identifying the presence of the carbonyl. So it's used to distinguish firstly if we have a carbonyl present, but it's also very useful because we can distinguish if we've got an aldehyde or ketone compared to, say, if we had another functional group that has a carbonyl, such as a carboxylic acid or an ester, because it will only give a positive result for our aldehyde or our ketone. All right, and then we'll go on to see how to distinguish between these two once you know you've got one of them, I suppose. So it uses this molecule called 2,4-DNPH, which means it is called 2,4-dinitrophenylhydrazine, which if I draw on the board here, looks something like this. So we've got a dinitro on a phenyl, like that. So NO2 is a nitro group. And then it has this funny looking group up here that looks like that. So that's our 2,4-DNPH there. Now, if we have a positive result, we will get an orange precipitate that forms. If we don't have a positive result, we won't get anything forming, and that will confirm the carbonyl in either the aldehyde or the ketone that we have. It is due to a condensation reaction between the carbonyl and 2,4-DNPH. Condensation reaction being the loss of a small molecule. In this case, that small molecule is water. So let me draw that up here. So we've got our DNPH, and then if we react that with our carbonyl, so if one of these R's is a hydrogen, we'll have a aldehyde. If they're both alkyl groups, we'll have a ketone. And what we do is we lose water, minus H2O, so we sort of form the water between that there, and then we form a new bond or new double bond between the carbon and the nitrogen into a molecule that looks something along the lines of this. So we still got this 2,4-dinitrophenylhydrazine section there, and then the end there, only we've lost the water and we now form a link there, and then whatever the rest of our molecule is. And this will precipitate out with a very distinct color, and we've confirmed that we have the carbonyl, and we can confirm that it's either an aldehyde or a ketone. If we look on here, that will look like this. We've got the 2,4-DNPH, we've got our carbonyl of our aldehyde or ketone, condensation reaction, we lose the water, we have the orange precipitate. That is the positive result for this test. This is useful as other classes of molecules with carbonyl groups will not form precipitates and will not give a positive result. For example, if we have a carboxylic acid or if we have a ester, these contain the carbonyl there, but they won't give the positive result, only the aldehyde or the ketone will, which makes it quite useful. So we can rule out the presence of other carbonyl type molecules, but what if we want to then distinguish between the aldehyde and the ketone? What we can do is we can use chemical tests that exploit the ease of oxidation. And in fact, this is something that we've seen previously, where we've said we can identify between primary, tertiary, and secondary alcohols. If you want to recap on this, there's a couple of videos ago in the hydroxy compound unit. But what happens is we can oxidize the alcohol into the aldehyde, and then that can be oxidized into the carboxylic acid. The secondary alcohol can be oxidized from that into a ketone, but the ketone can't be oxidized any further for reasons we'll see a bit later on. And then the tertiary alcohol can't be oxidized at all. So it's using a similar concept there. In fact, it's using the same concept that our aldehydes can be easily oxidized, but our ketones cannot. So we can use this difference in oxidation to identify between potentially an aldehyde or a ketone using some simple chemical tests that we will look at, starting with Tollens reagent. Named after German chemist Bernhard Tollens. A positive result will confirm the presence of an aldehyde, and a negative result can rule out the aldehyde and therefore could conclude that it could be a ketone. What it is, it's a solution of aqueous silver nitrate in excess ammonia solution. But what we're particularly interested in are the silver ions that can act as an oxidizing agent. So again, we said that the aldehyde is able to be oxidized. If I draw a picture of an aldehyde, yep, and I got the ketone there. So we've defined previously oxidation as either adding an oxygen atom, or conversely, it can be defined as removing a hydrogen atom. So our aldehyde is able to be further oxidized because we have the hydrogen that can be removed and we can oxidize it into the carboxylic acid, whereas our ketone is unable to do that because we don't have a hydrogen that we can easily remove. So it would require much harsher conditions if you wanted to oxidize that. So that's what the following two tests are exploiting in order to distinguish between the two. So if we have silver ions that can oxidize the aldehyde, the silver ions in itself will be reduced because we talked about the idea of an oxidizing agent. An oxidizing agent oxidizes the other thing, and the oxidation and the reduction has to happen concurrently. So in this case, the oxidizing agent itself is the thing that is reduced. And if we've got silver ions and we reduce that to silver atoms, we get a metallic silver atom, which gives us this very characteristic silver mirror. So the formation of the silver mirror will confirm that we have the aldehyde because again, the ketone is unable to be oxidized. So reduction to the silver metal atoms, so we've also got reduction as the gain of electrons, so we can show that there. And it will create this silver mirror, and the silver ions oxidize the aldehyde to a carboxylate ion due to the alkali conditions. So if we have the aldehyde, and if I oxidize this, I'll just do it down the bottom here. So my oxidizing agent like that. Now we could oxidize this through to the carboxylic acid, but we've said that this is a solution of a silver nitrate that is in alkali conditions. So what that means is if we're in alkali conditions, we're not going to form the carboxylic acid because the carboxylic acid is an acid, so it can be deprotonated to the carboxylate ion like that. So that would be the reduction, sorry, not the reduction, that would be the oxidation that is occurring. And again, the reduction is from the silver ions, which are our oxidizing agents. They are reduced to the silver metal, and this will give us a very characteristic silver mirror, which is the positive result. The silver ions are a mild oxidizing agent, therefore they're incapable of oxidizing the, I obviously haven't finished writing that sentence, incapable of oxidizing the ketone under these conditions. So simple test, we can first confirm we have the carbonyl in general, the aldehyde or the ketone carbonyl with the DMPH test. Then we can distinguish between the two with the Tollens reagent. Positive result means we have the aldehyde because the aldehyde can be oxidized and will form the silver mirror. That looks pretty cool. So like I said, the ketone has no hydrogen that can be removed compared to the aldehyde hydrogen. If we do want to oxidize the ketone, we require much stronger oxidizing agents. Another similar test which exploits the same properties of the inability for the ketone to be easily oxidized is this test using something called Fehling or Fehling solution. Similar to Tollens reagent, just with a different test, different chemicals. And again, it still uses that fact that the aldehydes can be oxidized easier, but the ketones cannot. Developed by German chemist Hermann von Fehling. Great name. So in this case, the thing that is doing the oxidizing agent is a solution of copper ions that can act as the oxidizing agent when warmed. And similar to the silver ions, the copper ions can be reduced from Cu2+ to Cu1+, and we observe a color change that corresponds with this. So we start off with the clear blue copper 1 solution, and that turns into an opaque, so that means you can't see through it, orange-red color as copper 1 oxide precipitates out if the oxidation can occur. If the oxidation cannot occur, if we have the ketone, we won't see any color change. So again, we will get the oxidation of the aldehyde to the carboxylate because we are in alkali solution. So for the same reason, we get the deprotonation with the toluenes, we get the deprotonation here as well to form the carboxylate ion. So very simply, we'll just see the color change. So we start with the Cu2+. This has a very nice blue color. And if this can be reduced, therefore acting as the oxidizing agent, then we will see Cu1+, which forms this sort of orange-red, orange-red type color. Now this will only be reduced if we have the aldehyde, if the aldehyde can be oxidized. For the same reasons that we said before, the aldehyde can be easily oxidized because we have the hydrogen. We can remove that hydrogen, add the oxygen, and form the carboxylate like that. If we have the ketone, so we got another R group there, we will have no reaction. If we have no reaction with the ketone, we will see no color change. So toluenes and phthalings do very similar things. The important things to learn here are, number one, what the oxidizing agent is. So the silver ions in the case of the toluenes, the copper ions in the case of the phthalings. And then to recall the color change or the silver mirror formation that occurs. So when the silver ions are reduced, we get a silver mirror that gives us the confirmation of an aldehyde present and rules out the ketone present. In the phthalings, we have the color change from the see-through blue solution to the opaque orange-red solution. Well, the orange-red precipitate, I should say more accurately, forms, again confirming the presence of the aldehyde, ruling out the presence of the ketone. Now, in order to prepare phthalate solution, it actually uses a copper complex that is quite unstable. So you can't just get a bottle of phthalates out of the cupboard. You've got to prepare two different solutions that you then mix in order to have the solution ready to go. So the first one is what's called phthalate A, which is a copper sulfate, has this deep blue color. The second one is phthalate B, which has this substance called potassium sodium tartrate, which is colorless. So then whenever you are ready to perform the test with the phthalate solution, you just combine these two and you prepare your copper complex that is then able to do the oxidizing. So yeah, the reason you do the two solutions is just uses something that's quite unstable, so you've got to prepare it when you're ready to use it. The final test we're going to look at today is also something that we've seen before, and it was this iodoform test where we use this triiodomethane to identify the presence of this, in this case, of a methyl ketone type substance, which if I draw out here, so it's the confirmation of having this kind of group there. Now, we've actually seen this before because we used it to identify or confirm the presence of a methyl secondary alcohol, which if I draw out here, we had the methyl secondary alcohol. And in fact, the first step in confirming this with the triiodomethane test was the oxidation into the corresponding carbonate. So essentially, it's the exact same thing, just without the first step, because we've already got the oxidized species here. Now, just one thing to be aware that we can have R as H. So in this case, we can have ethanal. Ethanal will give a positive result to this test as the only aldehyde that will. Similar to how ethanol was the only primary alcohol that gave a confirmation to the test. If you want to recap this, go back a couple of videos when we looked at the reactions of the alcohols there. But, I mean, we're going to go through it now anyway, so you'll probably be pretty good anyway. If we get a positive result, we end up with this yellow triiodomethane precipitate, which looks like this triiodomethane. So we got our iodo, got three of them, iodo, iodo, and then a H there. So this is a yellow precipitate, so this will confirm that we have this methyl ketone group present, similar to how we confirmed that we had the methyl secondary alcohol group. And remember, R can be a hydrogen, so there is the option that it is that ethanal. So the first step when we were looking at the secondary alcohol methyl group was to convert it into a methyl ketone, and then the rest of the test just operates as normal. The same triiodomethane will precipitate, will form in this instance. Ethanal also gives a positive result as it contains this CH3CO group, if that R is a H. So what are the steps involved? The first step, we have the halogenation of the carbonyl. So what I'll do is I'll keep these two steps up already, and then I'll just carry on underneath here. So what happens is we have the iodine in aqueous sodium hydroxide. This pen's a very strange one. Sodium hydroxide like that, and then what it does is it creates the triiodo substituted methyl section, and then all we gotta do is sever that to get the triiodomethane precipitate. So we'll have something like that. Again, R can be a H or any other alkyl group. And then after that, we've just got to, oh, there we go. There's some structural formulas showing it. So we go from the methyl ketone to the triiodo methyl ketone. And then the intermediate is hydrolyzed. Yellow iodoform precipitate is formed. And we get the breaking of that bond. And we end up with this. So we sever that bond with the hydrolysis. And we end up with the CHI3. So if you imagine breaking that bond and adding a hydrogen there. And then we end up, how am I going for space? I'll be able to squeeze it in here. We end up with the carboxylate ion like that, because we are in alkali conditions when we hydrolyze. So we will end up with the carboxylate because the carboxylic acid would be deprotonated. Negative ion, positive sodium ion from the solution, and that would be the precipitate that would confirm the presence of this group. And then if we get the melting point of this precipitate, we can confirm it's the iodoform, we can confirm it's the triiodomethane because it has a melting point of 119 degrees Celsius. And that concludes our lesson and our topic on the carbonyl compounds. What have we done today? Describe the use of 2,4-dinitrophenylhydrazine to detect the presence of carbonyl compounds, deduce the nature, whether it's aldehyde or ketone, of an unknown carbonyl compound from the results of simple tests, Fehling's and Toland's reagent, ease of oxidation, and then describe the reaction of CH3CO compounds with alkaline aqueous iodine to give the triiodomethane. Tasks for this lesson: pause, work through, and you will consolidate your understandings. Excellent work, as always. Have a great day. I'll see you when we start the next unit next time. See you later. Bye.